In this example, we'll look at the undamped motion of a mass on a spring. Consider a 16-pound mass that elongates a spring by 2 feet. We stretch it an additional 1 foot and set it in motion with an initial velocity of 2 feet per second, causing the position of the mass to oscillate up and down without damping. Let u of t be the position in feet of the mass t seconds after it is released from its equilibrium position. Let's first set up the initial value problem modeling the position of the mass and solve it to find u of t, and then find the amplitude of u of t, that is, the furthest position that the mass will be off of its equilibrium state. In this undamped case, we can model it by the differential equation m times u double prime plus k times u equals 0, where m is the mass and k is the spring constant. To find the mass m, we will use that the weight 16 is equal to mass times gravity, where gravity is 32 feet per second squared. Thus the mass is 16 over 32, which reduces to a half. The elongation length L equals 2, with the equation weight is equal to k times L, gives our spring constant k as W over L, which is 16 over 2, which is equal to 8. Putting this together in our differential equation with m equals a half and k equals 8, we get 1/2 u double prime plus 8u equals 0. And we can simplify this by multiplying by 2 to get u double prime plus 16u equals 0. This application also includes initial conditions, since the mass is extended an additional 1 foot, meaning that u of 0 equals 1, and additionally the initial velocity is u prime of 0 equals 2. So together, our differential equation and our initial conditions give the initial value problem u double prime plus 16u equals 0, with u of 0 equals 1 and u prime of 0 equals 2. To answer our questions about the application, we'll want to find the solution to this initial value problem that we set up, u double prime plus 16u equals 0, and u of 0 equals 1, u prime of 0 equals 2. To start, we'll find the general solution to the differential equation by solving the characteristic equation r squared plus 16 equals 0. Subtracting 16 and taking the square roots on both sides gives the complex roots r equals plus or minus 4i. In using the root r equals 4i, we can build the general solution u of t equals a times cosine 4t plus b times sine 4t. And now that we have the general solution, we need to impose the initial conditions to find the solution to the initial value problem. Using that u of 0 equals 1, and on the other hand, evaluating our function u at 0, giving a times cosine of 4 times 0 plus b times sine of 4 times 0, which reduces to just a, since cosine of 0 is 1 and sine of 0 is 0, we get that a equals 1. And to use the initial condition u prime of 0 equals 2, we need to compute the derivative of u. Here, u prime is negative 4a times sine 4t plus 4b times cosine 4t. Evaluating at 0 gives that u prime of 0 is negative 4a times sine of 4 times 0, which is just 0, plus 4b times cosine of 4 times 0, which is just 4b. On the other hand, our initial condition is that u prime of 0 equals 2, so we get that 4b equals 2, and thus b equals a half. So using that a equals 1 and b equals a half, we can write the position of the mass as u equals cosine 4t plus 1/2 sine 4t. In order to find the amplitude of this mass spring system, we'll want to write r as the square root of a squared plus b squared, which is 1 squared plus 1/2 squared, or the square root of 5 over 4, which reduces to the square root of 5 over 2. Additionally, we need to find delta, which is the arctan of b over a, which is 1/2 over 1, so delta is the arctan of 1/2, which we can't simplify any further. So we get that u of t is the square root of 5 over 2 times cosine of 4t minus arctan of 1/2, and in this form, we can see that the amplitude is r equals the square root of 5 over 2, as we wished to find in the beginning.